Okay, hello everybody. This is the fourth and last session for the Applied Networking Research Workshop 2020. I'm Mirja, and in the other video window you see my co-chair Roland. I will lead you through the session, who's now waving at you. I will lead you through the session, and for those people who haven't been in one of the three previous sessions, we will quickly go through some of the slides here as an intro. So the next slide, Roland is driving, is just very quickly to thank our sponsors. It's really important to make these things happen. Next slide. This is mainly for you to find in the proceedings. The proceedings are in the IETF data tracker. So if you look there at the slides, you will also be able to click on the link to join the Slack channel. So we do have a Slack channel for this meeting of this workshop on the SIGCOMM workspace, because this is a SIGCOMM or ACM SIGCOMM sponsored workshop. So you can use freely now the chat and also talk to the authors of the papers there in the chat. But if you have any questions later on, this Slack channel will be there, and you can find the authors there usually as well. All the program and the papers are also on the workshop webpage with the full PDFs of the papers, and you have free access to the ACM digital library for those papers. As all IETF sessions, this session will be recorded as well, and the recordings will be put on YouTube afterwards. So please be aware of that when you join the mic queue and put on your video. Next slide. Yeah, I just said mic queue. So for the question and answer part of this session, after each talk, we will use actually the mic, the queue tool provided by Meet Echo. So you can press this button you see on the picture, so the second button from the right underneath your name, which is a microphone with a little hand sign, to join the queue. And then the chairs will let you in and enable your audio to ask your question. Please use the queuing tool if you have any questions. There's more instructions about Meet Echo on the IETF webpage, so if you need further information, please go and have a look there. Next. Yeah, and that's where we are. So as I said, this is our fourth and last session. It's about monitoring and logging. It's two really nice papers. I'm really excited to still have these talks here. Yeah, it's only two of them. We only have 15 minutes. And we start with Robin Marks. Now I need to find the right window. There it is. So, I mean, actually, I don't need to read this because I know Robin quite well. He has been to a couple of IETF meetings, at least remotely, some of them. He is at the Hasselt University in Belgium, where he is a PhD student. And he's looking into HTTP as well as Quick and HTTP 3 and 2, basically now. And he is now talking about, I think, one of his favorite topics about logging for these kind of transports. So let's start the video.
Welcome to this presentation on debugging Quick and HTTP3 with qlog and qviz. My name is Robin Marks, and
Alessandro, can you start the video? I think you just missed us.
Yeah, just give me a sec because this room might be badly configured, so I might need to reload the configuration. Just give me a few seconds, please.
Okay, thanks. Okay, folks, I have some bad news from Meet Echo. Welcome back. Apologies, folks. Something went pear-shaped with the Meet ecosystem. Let's give everybody, so we have 69 people back in the room. Let's give everybody 1 or 2 minutes to join again. And of course, we will make up for the time at the end of the session.
Yeah, I believe if people just did nothing and were just waiting for the closed room, they should be automatically back. So, but
I see 70 people already, 71, so it's going up. And the people on Slack are also confirming that it's working again. Ha! Every conference has to have its technical problem. Normally, it's somebody trying to desperately plug in their laptop to a projector.
Yeah, it's just like virtually, it's a little bit more a problem when everybody's away and you don't have a communication channel anymore.
Yes. It seems that we're back online and people are coming in quickly. So Robin is joking about it. Shall we start Robin's video?
Yeah, I think we're ready.
Okay, Alessandro, go ahead.
Welcome to this presentation on debugging quick in HTTP3 with QLOG and QViz. My name is Robin Marks and I am a very large Lord of the Rings fan. And I'm telling you this because recently I have had an epiphany, and that is that the quick and HTTP3 specs are really quite bulky. Even if you look at just the core 6 documents, their total page count is already well over that of Tolkien's book The Hobbit. And to make matters worse, while The Hobbit is generally considered a children's book, I think we can all agree that most of these texts are more at like the Lord of the Rings reading level. And some, like the TLS and the recovery drafts, are more like Tolkien's Silmarillion, by which I mean they are more the area of actual wizards and not intended for us mere mortals to understand. And I kind of learned that the hard way about 2 years ago when I myself was implementing Quick and really struggling. And I thought by myself, it would really help me if I would have access to some tools, things like TCP Trace. It didn't exist yet for Quick at this time, so we simply decided to build it ourselves in what is now called the QViz tool suite. This worked well for us and we wanted to make it available for other implementations as well. But that's kind of where we hit some sort of a roadblock, because we noticed that we were going to need a common input format to get data into our tools. We first tried this with packet captures, which works, but they miss a lot of internal implementation state. Things like the congestion window or round trip time measurements, or why exactly a packet was dropped. These are all things you do want to know when debugging. These are things that are also available inside what you call the ad hoc logs, so the command line logs or the console logs. The problem with these, however, is that they are often unstructured and they are also different across the implementations. We did write a few parsers for different ones, but it quickly found that that was no fun at all. So what we did instead is that we proposed, how about everyone simply log in the exact same format, and if we make this a machine readable structured format, then we can use this as input for our tools as well. And this is what we called the QLOG format. And we proposed to use as the basis for this was JSON. because we think it's like the best of both worlds. It is machine readable, but also human readable, and it's also very flexible because it is inherently schemaless. You can very easily add or remove things without breaking it. To give you an idea what QLog looks like in JSON, it's really quite straightforward. Every event simply has a timestamp and a category and some event metadata associated with it. Now, we thought it was a good idea, but let me be honest, we didn't actually think anybody was going to implement this just to make use of our tools. And I must say, I haven't been, I'm so very happy I was proven wrong, because now, 2 years later, it turns out about 2/3 of all quick implementations do actually output QLog, with several more having plans to support the format over time. Facebook has even deployed this into production, and they report logging several billion QLog events every day. Given this, we thought the moment was ripe to try and figure out why exactly this has turned out to be an unexpected success. So we performed an expert survey with eventually 28 participants, all of them either active quick implementers or academic quick researchers. We also did an in-depth interview with Facebook to find out what works and what does not in their practical deployment. We didn't just ask about QViz and QLog, it was more about quick and tooling in general. I'm not going to bore you today with all of the statistical details and all the different answers. You can find those in our paper and on our website. I have kind of summarized this for you into 4 points, and we're going to start on the top there, because one of the main reasons people implemented QLog was indeed to make use of our tools. So let's look at those. The first tool is our sequence diagram, which plots a connection trace on a vertical timeline, where each QLog event is one of these squares and each packet sent or received is one of the directional arrows. And you can click on them to get more information on what exactly was contained in these packets. The internal endpoint state is visualized on the sides, as you can see. This is already quite interesting, but one of the innovations that I think we added is the ability to load the same trace but from a different vantage point. In this case, we now have client and server, and this allows us to accurately visualize the round-trip time on the connection, where there was packet loss and also reordering in transit. This setup has helped us a lot to debug Quick's complex encrypted handshake, which is quite easy to get wrong in the implementation and can easily lead to deadlocks if there are problems with the recovery and retransmission logic. Our colleagues from UC Louvain have used this concept as well in their implementation of the multipath quick extension, and they're also listed as co-authors on our paper, because they have extended QLog to add per path information to the events, and they also implemented, for example, this custom sequence diagram tool, which visualizes individual paths as differently colored arrows. So, for example, the first path is the cyan combined with the red, and the second path is the green combined with the purple. And what we will see here in this trace is that we try to establish this second path, but that because of the testing conditions, the path challenges and responses actually are lost in transit every time, meaning that the second path cannot be established. What we would expect the implementation to do is to fall back to the initial path to complete the file transfer, which clearly does not happen here. This is quite easy to see when compared to the second trace, in which we have the exact same situation, but here, after a while, we see that the implementation indeed falls back to the initial path to complete the file transfer. Simply using different colors for these arrows per path allowed them to very easily debug a lot of different multipath issues using this type of tool. The second tool that we have is our congestion graph, which is very similar to TCP traces time sequence diagram, where in the blue we have our data sent, and then in green we have the accompanying acknowledgements, and the red indicates that we had a packet loss event. We also show flow control information here, and of course, because we're using QLog, we can also show the actual congestion window and bytes of flight, as well as on the bottom here are round-trip time measurements accompanying those as well. This allows us to also quickly observe some of weird anomalies in this trace. For example, here at the beginning, there was a period where we were sending nothing at all, even though we had plenty of congestion window allowance. This is because of the flow control here in pink, which only updated really late, causing to a delay in the send rate in this trace. This tool has been used extensively by others to implement and verify several new congestion controllers. For example, Cloudflare has a very nice blog post on how they added cubic and high-store support to their quiche implementation. Again, our colleagues from UC Louvain have taken this to a slightly different direction, splitting out these different congestion control metrics per path. So here each column is a different path. On the left we have the initial handshake path, and then 2 more paths, each with different round trip times and bandwidth that are being used to transfer a single file. Splitting these out in this way allows them to find problems with their multipath logic quite efficiently. The third tool that we have is a multiplexing diagram. This is needed because Quick uses just a single connection, but it still wants to share bandwidth between different independent streams. What we do here is to assign each stream an individual color and then plot different stream frames, or let's say packets, on the timeline. And if we get this kind of top-level visualization here, this means that probably the files have been sent sequentially, say first in, first out. This is quite different from this next trace, where we see much more of a smudgy colors show up, or maybe a rainbow, and this is because here the server was using a more of a multiplexing, a round-robin multiplexer rather, switching between the streams for each packet. However, it's weird that if we zoom out here, we do see some areas in which this server seems to be using a sequential scheduler as well. And this can be explained by looking at the bottom part here, because the black areas indicate that this data has been retransmitted after being declared loss. So we see that here for retransmitted data, apparently the server does switch to a more sequential scheme. However, we do have some areas here at the start that are sequential but do not correspond to retransmissions. And this is exactly the kind of bug that you tend to find with this kind of visualization. And this turned out to be weird interactions between internal buffering logic and flow control limits, causing this weird behavior. This tool is now being used extensively to debug implementations of the new HTTP3 prioritization scheme, which allows you to indicate for each stream whether you would like to send it sequentially as the first 8, or whether they can indeed be multiplexed on the wire, as we can see happening here for the last 2. The final tool that we discuss in more depth in the paper is the packetization diagram, which allows us to show how exactly HTTP3 level data is packed into quick stream frames and then into larger quick packets. This allows us to show protocol overhead to show up as these large white areas to get an idea of the overall protocol implementation efficiency. So now that we know what we can do with the QVIS toolset, let's look at why people like the QLog format itself. And a lot of that can be summarized in the idea of it being very flexible. So QLog defines a lot of different events and their fields, but most of them are actually optional. A good example is seen in the packet drops event on the right there, where every field is actually optional, indicated by the question mark in the schema. This means it's very easy to leave out some of the events you don't want to log, or indeed to add new ones if you need something specific for your implementation, as we've seen, for example, with the multipath as well. And this has been used extensively in practice. I think most core users actually log their own kind of dialect of QLog in practice. The nice thing about that is they can do this without having to wait for me to update QLog or even QVIS, because the tools were made with this flexibility in mind, and they will simply show new events or new packet types or new frame types and quick in the tools as they are. So people have been able to iterate on this really quickly. Another aspect of this with JSON is that it can be used for other use cases as well, or to make things easier. For example, Facebook doesn't log full QLog files. They log each event individually to a database, which makes it very interesting for them to later just query on a per event basis to find interesting traces to analyze. They've also been using this, as well as IOQuick, to do some unit testing in their implementations. For example, is the SpinBit implementation working? We can simply look at, are there SpinBit related events in the QLog? There's a simplified example on this slide from move files as well, where they test some congestion control state changes, where they trigger in the tests an application limited condition and then also check that it actually went away. So I thought this was a very interesting use case that I hadn't anticipated before working on it. The last example I wanted to say is that it makes it very easy to transfer between different structured formats. So we, for example, have a PCAP to QLOG converter, allowing you to load PCAPs directly into QFIS as well. It also makes it easy to tamper with new protocols. People have been using this for DNS over QUIC as well. And we ourselves, as we've seen, have used this to do TCP, TLS, and HTTP2 debugging with the same tools as well, where we get most of our stuff from the PCAPs and then use eBPF kernel probes together with some HTTP2 application logs to get like a full QLOG with internal state as well. So this is what people liked about the QLOG format, or at least some things, but there are also some things they don't like. And the main pushback that we've always gotten is that people are afraid that it's too slow and too large because we use JSON. And you might think, well, is that really a problem? Because if we're debugging locally our implementation, this shouldn't really matter in practice all that much, right? But it's time to consider a fuller quick deployment timeline, right? Because debugging the implementation is only the first step, which we've kind of done by now, and now we're moving into actually deploying these implementations, where we need to debug that deployment first, and later, of course, fine-tune it for performance. And for those cases, if you want to do analysis on that, then of course, yes, you will need to scale up to run with thousands or even millions of connections. And you could think, well, maybe, for this use case, we might instead just go back to those packet captures, right? Because they contain most of the data. The problem with QUIC is that it's almost fully encrypted. While with TCP, things like your sequence number or flow control limits are in the public TCP header, that is no longer the case with QUIC. So for QUIC, you would have to store the entire packet capture on disk, which can get quite large, and afterwards decrypt it to be able to get this information, which opens up some privacy and security concerns, because you first need to store your TLS decryption keys, and after you've decrypted the PCAP, you not only have access to the QUIC metadata, but also the full user data as well, because they are not separately encrypted. Another option that has been discussed would be, to add a couple of bits to the public QUIC header to help with some things. We all know that's a very contentious issue, and I think that even if they were added, they wouldn't really help with many of debugging, of in-depth debugging use cases that we might have in practice. So the idea was, or would be, how about we use QLOG for this use case as well? And then you can start to understand, yes, if we want to do that, then we indeed need to make sure it scales. And many people say, in that case, we want to use a binary format instead of JSON. To keep the file size down and also to make it faster to, for example, serialize. I've always kind of pushed back on that because I feel that binary formats are typically much less flexible. They typically use an upfront defined schema, which doesn't allow you easily adding or removing events at will. Another counter-argument is that Facebook, they've actually deployed QLOG in its JSON format, and they're logging billions of events per day. The caveat there is that, those are mostly server-side events. They've also said that indeed it becomes quite difficult sometimes to upload client-side logs because they can be quite large. What they also indicated, though, is that they try to upload these at this time without compressing them first. And this makes a big difference. To give you an idea of what we're talking about here, these are some numbers for a download of a 500 megabyte file. And we can see that the PCAP indeed is very large. But to be fair, the JSON QLOG is also quite large. And we can get that down a little bit by using CBOR, which is the binary form of JSON, which is still very flexible, but as you can see, also doesn't really bring down the file size that much. And you can see indeed the protobuf, which is one of those optimized binary formats, really helps bring the file size down. However, this is before compression. If we start adding compression, I think it's quite a different story. Where the CBOR and the binary formats are actually very similar in what they end up with, right? Still, And this is what I like about the IETF and hate about it as well, is that people kept on giving pushback, really wanting that binary option for qlog as well. And so our current approach is to allow that too. So what we're doing is more decoupling the qlog events and the schema from the actual format. The documents will still assume you're using JSON, but we're going to make it a lot more easy to make it compatible with binary schemas, so that people that really need this for their production setup can indeed move to more that kind of thing, with still keeping the same qlog definitions as you use in JSON. This should be in the next qlog version that is expected to drop either this week or next. Of course, this will need some more evaluation over time to see if it actually works, but we're hopeful this will resolve most of the issues people had. So in conclusion, I think we can say that the tools have been a huge success. They've turned out to be very useful, not just for us for research, but also for actual implementation debugging. The qlog format has potential, but we still need to tweak a couple of things there to make it usable in the wider deployment sense. But we have good hopes that this will work. There are some future challenges still, of course, that I'm hoping the IETF can work with. It's still unclear if qlog can also solve the network operator use case, because they typically won't have access to the qlogs directly. Maybe we can share some of those endpoint qlogs, but then you need infrastructure for that as well. Interestingly, there are other people that have come up with a very similar, I think, proposal independently, which is being discussed in the next session in IPPM after this, if you're interested. Another very important part of all that is we should start having some privacy and security guidelines on how to anonymize qlogs, for example. Happy to say that, for example, Christian Huytema has been contributing in that effect as well. Finally, I think this has shown quite a bit of potential, not just for Quick and H3, but also maybe for other protocols, which is a discussion I'm very eager to have with you all. And with that, I would like to thank you for your attention.
Okay, thank you very much. So my fan is just running crazy, so if you have some background noise, I'm sorry for that. But other than that, we're, I think, ready for questions. We're a little bit behind time, but unsurprisingly, but I think we can go 5 minutes over, so let's have some questions. And there's Simon.
Hi, very nice work. Thanks for doing this, and I'm glad you have such a good uptake. And also, it's interesting that this seems to be to confirm the end-to-end arguments that you can do these things at the end systems. Yeah, also important input for discussions on how to modify the protocol. As an operator, I should probably be arguing. Oh, sorry. Oh, you see me now? Sorry, it's the first time I'm using this. I should probably be arguing in favor of things that that allow us to do debugging from the midpoints. But honestly, we sometimes do debugging performance issues, and generally, at some point, you have to go to the endpoints. And it's super good to know that that even with Quick, we'll have possibilities to do that. So it makes me very happy. One question I had, and I'm sure it's mentioned in the paper, is can we expect to backport these things to older transport protocols that are implemented in kernels and not just Quick?
Yeah, can you hear me?
Yes.
Yeah, okay. So yeah, in the paper, indeed, we discussed that we have been making a proof of concept for that for TCP. So using the eBPF kernel probes to get to the congestion window and round trip time estimates like that. It's not super far along yet, but the proof of concept seems to indicate it will work. So that's definitely something we're interested in progressing, yes.
Excellent, thanks a lot.
Yeah, more questions or comments? I don't have any question. I think this is all crystal clear, and I think we can just right away go to the HUM to form a working group. Yeah, so thank you, Robin. and see you at some other IETF meetings. Bring back your work, hopefully.
All right, thank you.
Oh, wait. There's Jana.
Oh no, oh no.
Oh, hang on. I feel like I'm a newbie to this interview, even though it's been a whole week. Thank you for the presentation, Robin. And I just, because there are no other questions, I also just want to add that this has been a super useful contribution to the community in general. I think it's shown its value, as Robin already pointed out. But I think it's important to note that this is kind of fundamental to transport work, being able to have access to traces into this sort of stuff. And Robin's work not only has shown that we can do that for Quick as well, encrypted transports as well, but it's also shown that you can get a lot more information by doing endpoint level logging and doing it at scale. So thank you for the work again.
Thank you.
Okay. I think now we actually move on because we anyway don't have time. So thank you. We're going to the next talk. The talk is held by Ioana, and she's a postdoctoral fellow at the SimilarMed Research Center in Oslo. Prior to that, she was holding her PhD from the University of Oslo on measuring the adoption of IPv6. So also very interesting topic for this community. So in general, she's focusing her research work on measurements of reliability, resistance, and security on the internet. And with that, we will start our very first or very last talk for this workshop.
Hi, my name is Ioana Lepădariu, and in this video, I'm going to present our work entitled On the Accuracy of Country-Level IP Geolocation. IP geolocation maps physical locations around the world to IP addresses. Many commercial entities rely on geolocation services to provide customized services to their end users based on their location. At the same time, knowledge of the location of the IP addresses can be used to understand the underlying physical paths that connect endpoints in the internet. This information can be leveraged to study BGP threats, interdomain congestion, and censorship. When talking about IP geolocation, there's a clear distinction between geolocating the edge and the core of the internet in terms of accuracy. IP geolocation has been an active research area for some time, and thus there is a large body of work on this topic. Existing geolocation approaches can be divided in two categories: commercial geolocation databases like MaxMind and IP2Location, and measurement-based approaches that aim to identify the location of IPs based on either active measurements and/or by leveraging geo-hints in the DNS names. Current IP geolocation studies focus on either new or improved IP geolocation approaches or on evaluating the existing geolocation approaches against a set of IP addresses. In this work, we investigate the accuracy of existing geolocation approaches in geolocating end-to-end IP paths. To this end, we perform a control measurement study to collect IP-level paths. The figure shows the country location of the end sites in our measurement setup. Most of these are multi-homed via an educational network and at least one ISP. A significant fraction of the end sites offers IPv6 connectivity. We mark with green the end sites that are IPv4 only, and with red the ones that are dual stacked. For our study, we run traceroutes between these locations over the span of 6 months. In 2018, we further employ 5 geolocation approaches to geomap the collected IP paths. We list on the slide these approaches. We use the non-commercial versions of two popular datasets, MaxMind and IP2Location. Our choice of the non-commercial version is motivated by the fact that we are interested in country-level IP geomappings, and recent studies have shown that there are minor differences between commercial and non-commercial versions in the country-level IP geolocations. We also use information regarding the country from the regional Internet Registry's allocation and assignment files. At the same time, we use two recent geolocation methods, IPMap and HLOC, that employ active measurement from vantage points to determine the location of IP addresses. RIPE's IPMap relies mainly on RTT measurement from RIPE Atlas probes. HLOC also uses the RIPE Atlas platform, but prior to this, it extracts geohint from the IP's DNS names to select the set of probes that is going to use to perform the measurements. The first step that we take in our analysis is to understand the geolocation dataset coverage of the set of IPs that are present on our collected IP paths. The plot shows the percentage of IP addresses mapped by each of the 5 geolocation approaches for 2 months, May and September 2018. The geolocation datasets, Delegation, MaxMind, and IP2Location appear to have a high coverage, as these map more than 80% of our IP addresses to a country. IPMap covers more IPs than HLOC, which is probably due to HLOC's dependability on the existence of DNS names and geohints in the DNS names for mapping the IP addresses. Also, HLOC rejects half of the geomappings, indicated on the plot by the empty area. This happens when certain conditions imposed by HLOC are not satisfied. For example, HLOC is going to reject inferred geolocations that are over 1,000 kilometers away from the RIPE probe used to determine the location. For many of these rejected mappings, the root cause comes from the fact that DNS names contain multiple geohints, and HLOC ends up selecting the wrong geohint. Our next step is to analyze the overlapping between the different IP geomappings. For this analysis, we look only at the mappings obtained when using the 3 geolocation datasets, that is Delegation, MaxMind, and IP2Location. The top part of the slide shows the percentage of IPs mapped by the datasets to a country in May 2018. The dark gray color indicates that the IPs are geolocated in all 3 datasets. The bottom part of the plot shows the geolocation agreement between the different IP geomappings. We mark with orange the percentage of IPs that are mapped to the same country in all 3 geodatasets. We note that most of the IPs that are covered by the 3 geolocation datasets are also mapped to the same country. However, we find that some IPs have partial or complete disagreement between the country-level IP geomappings, and we are further interested in understanding why these disagreements occur. However, to understand this, we need a clear idea about the location of the IP addresses. And to find this location, we propose a very simple method for geolocating IP addresses that relies on a very simple idea. A location of a router can be greatly narrowed down if we probe it from inside its AS. To this end, we take the following steps. We first determine the owner and the possible location of the IP address by extracting information from whois data and DNS names. Next, we use this extracted information to search for suitable vantage points in order to trace a route to the IP address. We use as vantage points looking glass servers. Depending on the looking glass query response, we either select another vantage point or we stop the active measurement if we consider that we are topologically close to the probe IP. And we make this decision based on the number of hops and the RTT value obtained when probing the target IP. We show how this would work for a given IP address. We start by extracting the owner and location for the IP address as well as the AS number. In our particular case, the IP is owned by Cogent, and as possible location for the looking glass, we find this to be Oslo, Norway. We use this looking glass to query the target IP. And when parsing the query response, we find that this IP is within 1 hop away from the looking glass and under 1 millisecond. So we map the country location for this IP to Norway. We use this approach to determine the location of the IPs for which we found geolocation disagreements, and we investigate the root cause of these disagreements. Our analysis finds that these IPs can be classified in 2 categories: IPs that are owned by global organizations and IPs that are acquired through merge and acquisition. We show on the slide one IP for each such category. In the first case, the IP is owned by Level 3 and is mapped to Great Britain by Delegation and MaxMind and to the US by IP to location. The second IP is currently owned by Cogent, but was previously owned by a US company which was acquired by Cogent. Each geolocation data set mapped this IP to a different country. We further want to understand how the IP geolocation disagreements impact the country level end-to-end path geomappings. We find that about half of our collected IP paths have similar geomappings. We mark with purple on the plot these IP paths. For the remaining paths, we find that the geomapping disagreement is mostly due to IP to country mappings disagreements that appear along the path. Next, we analyze the possible implications of the incorrect geomappings of the end-to-end path. Specifically, we explore how such errors can impact the inference of path thromboning and detours as well as causing missing countries. Due to our measurement setup, a high percentage of the paths start and end in Norway. In the case of IPv4 paths, we find no evidence of path thromboning in any of the considered end-to-end geomappings. In the cases of IPv6 paths, we find one such case when considering the MaxMind geomappings of the end-to-end path. Using our looking glass approach, we actually geolocate the IPs that cause this path thromboning in Norway. So, in this case, the false positive is caused by an inaccurate IP to country mapping into the MaxMind dataset. To analyze path detours, we consider IP paths that start and end in the same region. For such paths, we expect that the path geomappings indicate that the path remains in the same region. So, when considering a path that starts in Norway and ends in Germany, we expect that all the hops along the path are mapped to locations within Europe. However, in the case of the delegation geomappings, we observe that the path goes from Norway to Great Britain, US, back to Great Britain, and then finally reaches Germany. When we use the MaxMind dataset, the path jumps also to US, but on its way back to Europe, it does not cross Great Britain again. And when using the IP to location geomappings, the path also appears to jump to the US, but it does not cross Great Britain at all. Mapping the path using our looking glass approach shows that the path remains in Europe and goes from Norway to Germany. The path detours that were seen using the three geolocation datasets are due to level 3 IP addresses that are mapped incorrectly to Great Britain and US. Our final analysis investigates whether wrong mappings result in leaving out one or more countries on the path. We first check how many paths have missing countries. We find that a high percentage of the paths appear to miss at least one country when we compare path geomappings generated using the three geolocation datasets. We show one such example between China and Norway that traverses three organizations: China Unicom, Cogent, and Broadnet. In the delegation geomappings, the path starts in China, traverses US, and then reaches Norway. Using the MaxMind dataset, we see that the path does not jump directly from US to Norway, but it traverses first France. The IP to location geomappings place the path in China, US, Canada, and then Norway. So, when comparing these three geomappings, we find that France and Canada are missing countries. However, while mapping this specific IP path using our approach, we find that the IP path actually consists of a series of countries. Specifically, the path starts in China, goes to the US, Canada, Netherlands, Germany, Sweden, and finally reaches Norway. So, countries like Germany, Netherlands, and Sweden are completely missed in the other IP geomappings. In this work, we investigated the accuracy of existing geolocation datasets in geolocating end-to-end IP paths. Our analysis shows that popular geolocation services appear to heavily rely on data from the Internet registries. We also find that geolocation datasets tend to wrongly map IPs that belong to ASs with global presence and IPs that change ownership due to merge and acquisition. We also find evidence that such IPs can falsely indicate path tramboning or path detours. Also, the geolocation databases appear to miss or add countries to the end-to-end path. Using the same datasets, we geolocate 1 week of RIPE Atlas traceroute data. Our analysis of this larger dataset validates our previous findings. We devise a simple method for improving the IP geolocation in the core of the internet, and we are currently working on improving this method.
Okay, thank you very much. This was our last talk. We are already 2 minutes over time, but given the problems we had at the beginning, we can still take 2 minutes for questions. And there was already somebody in the queue earlier, so if that person wants to rejoin, perfect. We go with the first question. Carlos.
Hi.
Just go ahead and speak, yeah.
Okay. Hi, my name is Carlos. I work for LACNIC, one of the regional internet registries. I wanted to make a point about the meaning of the delegation files, which is something that comes up again and again during IETF presentations. I wanted to clarify the semantic of the country code field in the delegation files. The country code field doesn't mean geographic location, it means legal location. I mean, when you see like US or UI or NL or whatever, what it means is that the organization that has that resource has declared to have a legal address in that country. It's expected that about, I would say, between 80–85% of those things match, but there's no guarantee that they will match at all. Okay.
Thank you. That's actually good information. Maybe because I'm also sharing the group, maybe you can actually send an email to the Mabergy mailing list, which is a research group looking into measurements. As you're saying, this comes up over and over.
Yeah. Yeah, sure. No problem.
Thank you.
Yeah,
So can I comment here a bit?
Sure. Yeah, it's for you.
Yeah. So thank you for clarifying this. But also in the paper, I do acknowledge this. So I acknowledge the fact that we expect the country in the delegation to be somehow, to bring like some error there. And we take this into account just to try to understand, because we thought it would help us understand the root cause of the errors. Yeah, so we acknowledge like this very clearly in the description of the data sets.
I will take Miriam's recommendation. I will send an email. And one of the things that we sometimes gets us in hot water is that people say around that the delegation files are wrong because the country code doesn't match. But the thing is, the country code does match the contract. The contract that is signed between the registry and the organization is obviously matches because it matches some form of legal document depending on the region. Yeah, thank you very much. Do I have to do something to
no, we can kick you out.
Okay.
Thank you.
Please kick me out.
So we have one more question, Sanjay, who seems to have audio problems. Can you try again, Sanjay? It's coming in and out. You can also
chat, Sanjay. We'll read it out.
Let me ask a quick question in the meantime, because I did some similar work on geolocation and trying to figure out the accuracy of geolocation on a more fine-grained scale. So did you look at anything below country level?
No, we don't report anything here below country level.
Is that something of interest for you, or was the?
I think the overall idea here was we were basically after country level geolocation, but this idea, this very simple idea that was sketched, I think it would work even like lower, like city level probably, where like this is just like a sketch of an idea that we have. And I'm currently working on improving it, so I think it would work.
Okay, that would be interesting. So I don't see anything from Sanjay in the chat, and he's also not in the queue. I guess he still has audio problems, so maybe Sanjay can just go on Slack or send an email.
Yeah,
and with
sure.
that, thank you for your presentation. We kick you out of the video here. Yeah, and that was the last talk of our workshop. Thank you not only Joanna, but like everybody who presented and sent papers. And we have a bunch of other things because this was a not planned and like unusual situation. So we had a lot of help and support from the secretariat, from Colin, of course, the IETF chair. And a big part of the work was done by the program committee. We had the name of all the members at the very first session. So if you want to look up and send a thank you email, you can do it right away. Again, sponsors also, even for the virtual meeting, we need some support for financial costs. And of course, we also have the ACM and SIGCOM supporting us with the publications and also money for some extent. And lastly, we want to also thank Meet Echo, because, you know, even so we had this little crash today, they did like a great job to actually extend functionality for us to make the video running and these kind of things. So they've been very busy the last couple of weeks and especially this week. So big thanks there because I think it worked out really well at the end. And I would also like to thank my co-chair because it was actually a lot of fun. Even so this wasn't planned this way, I think I enjoyed it quite a lot. And that's the end of it. Roland, you have the last word.
Yes, I would like to thank my co-chair as well. It was great to work together, and I would actually like to do it again. And we have Lars who wants to say something. So shall we let Lars in? Yeah, we should. Go on then. There you go, Lars. You're on.
From the steering committee, I want to thank you guys for doing an excellent job as program committee chairs. This was really good. And now you're on the hook to find us 2 new chairs that will do an even better job next year.
Nobody told us.
We are going to plan on having another one of these probably next summer by default, unless something changes.
Yeah, hopefully back together in the same room.
Sadly not.
And Colin can let himself in.
I can let myself in, yes. Superpowers, I'm afraid. So I just want to echo what Lars has said. Thank you. This has been an excellent workshop. You've done a great job as chairs. Thank you to all the speakers, everyone for submitting papers. There's some really nice work here, and I very much look forward to the workshop next year. Thank you, everybody.
Thank you.
Thank you. Bye-bye.
Bye.